Imagine that you are playing one unbanded slot machines in casino. There are a lot of machines, and each machine has different probability of winning money. Your goal is to find a machine that has highest winning probability and win as much money as you can. This is exactly the K-Bandit problem. Our goal is to train a software agent to win maximum money using reinforcement learning. However, please note there is one important assumption. The agent has unlimited money and can never go bankrupt. Let's create a 10 machines test bed first. Each bandit machine has its own reward distribution, as shown in this figure. Some machines have positive mean reward, while some have negative mean reward. Let's define the optimal action value function Q star of A, which means the expected reward of performing action A. In our case, it's playing 8 bandit machine. The expected value of a Gaussian distribution is its mean. So, for example, the Q star of 1 is the mean reward of machine 1, and the Q star of 2 is the mean reward of machine 2, and so on. The optimal action value function Q star of A is unknown, so our goal of learning is to learn the action value function Qt of A. During our trial and errors, we can try to estimate the true returns of the machines. In other words, we don't know the true rewards, but we can estimate them by playing the machines. So Qt means the estimated value or reward of action A at time t, and we keep updating each time we play. Let's formulate Qt of A. Qt of A is actually the sum of rewards when action A is taken prior to time t, divided by the number of times action A taken prior to time t. We can actually use the indicator function to represent the Qt of A. This one, capital AI equals A, is actually called indicator function. It means the function is 1 if capital AI equals to A, or 0 otherwise. So using indicator function, we can formulate the action value function Qt of A, and our learning goal is to let our estimated value function approach to the true optimal value function Q star of A. This is our learning goal. How can we choose which action to take? Remember the epsilon greedy method. Greedy means we always select the action with max value, so we can formulate it as argument max A Qt of A, which means we select the action max Qt returns the maximum value at time t. So epsilon greedy is actually select the greedy action 1 minus epsilon of the time, while randomly select actions epsilon of the time, and let the agent to explore other probabilities. In other words, in our case, let agents to play other machines instead of this optimal machine A. Here is the simulated performance of epsilon greedy with different epsilon values. This is the average rewards over 2,000 rounds. Each round plays the machine 10,000 times. The green line is with the epsilon equals 0, so it's totally greedy actions. We can see that it saturates at average reward to 1 and never improved because it never explored. The red lines is the epsilon equals 0.01. It gradually improve its rewards because it only explores 1% of the time. The blue line is epsilon equals 0.1. It improves faster than the red lines, but we can see that the red line is approaching to the blue line slowly. Here is the average optimal actions selected by different epsilon greedy. Unsurprisingly, epsilon 0.1 select most optimal actions and keep improving. On the other hand, epsilon equals 0, the greedy approach stuck and select less optimal actions than the other two epsilon greedy method. Now let's see how to update the action value Q. Now, for simplicity, let's consider only single action. Let Q1 denotes the estimate value of single action after it has been selected n-1 times, and Rn is the reward of single action. Then the relation between Rn and Q1 can be formulated as this. So it's actually the sum of all previous reward divided by the number of selected times. A naive implementation can be recall all the previous rewards and calculate the average each time we get a new reward, but that will be very inefficient. Actually, Qn and Qn plus 1 has a recursive relationship. Let's derive this update rule. Let's start from the Qn plus 1. So Qn plus 1 can be formulated using sigma. Sigma means the summation of all Ri and I from 1 to n. And we can separate the Rn from sigma and make the final Ri as n-1. Then we can multiply with n-1. We can add this extra term. So actually, this item is equal to Qn, right? Is equals to n. So we can write this formula as Rn plus n-1 multiplied by Qn. And when we multiply n-1 with Qn, we can actually move this term out here. So actually we find a perfect recursive relationship between Rn plus 1 and Rn. And we only need, whenever we do a trial, we only need to recall the previous value Qn and calculate the difference between the new reward Rn and divide it by the number of time steps. So if we have this update rule, we only need to remember two values or three values: the Qn, the number of time steps, and Rn, which save a lot of memory. We have derived the update rule of Qn plus 1, which is equal to Qn, right, plus the current reward Rn minus Qn. So it's the difference between current reward and the current value, then divided by n. So the 1n is actually called step size. However, this formula is only suitable for stationary problem. which means the environment is static and the reward probability never change. This assumption is unrealistic. In practice, the environment are dynamic and always changing. So how can we track a non-stationary problem? In fact, it's very simple. We can use a constant step size alpha. So this trick is simple and effective. So we can now derive new update rule. So now we have alpha Rn plus 1 minus alpha Qn, right? And we can continue to use Q minus 1 to represent Qn, right? So it's now alpha Rn minus 1 plus it's Qn minus 1. Right, so we can multiply the alpha minus 1 into this formula. Plus the square of 1 minus alpha multiplied by Qn minus 1. And the Qn minus 1 can actually be rewritten by the recursive rule, right? By Qn minus 2. So eventually we will have our formula as 1 minus alpha to the power of n multiplied by Q1. And the sum of alpha multiplied by 1 minus alpha to the power of n minus I multiplied by Ri. So this is the final equation of our new update rule for non-stationary problem. So actually, we'll see that later that the constant step size doesn't converge. But this is exactly what we want. We want our value function can track the latest update of the reward. It constantly change and doesn't converge. So the constant step size is what we want. The new update rule is called exponential recency weighted average. We can observe that actually Qn plus 1 is the weighted average of past rewards, Ri, and the initial estimate, Q1. It is called the exponential recency weighted average because, in fact, the multiplier of Q1 and the multiplier of past rewards are actually the sum of those two multipliers are actually equals 1. So it's a weighted average. You can prove this by yourself. So how the selection of initial value Q1 affect the final learning results? We can run a simple test in our TAM-on Bandit machines test bed. We can set the Q1 to a high reward. Suppose we set it to 5. Recall that the optimal action value Q star are selected from a normal distribution with mean close to 0 and the variance 1. So the initial estimate of plus 5 is very optimistic. So this optimistic actually encourage the action value method to explore a lot, because whatever he select is less than the target value. So it's actually the optimistic initial value actually encourage the agent to explore more at the start, and eventually it will find a good strategy. But in practice, the optimistic value not necessarily work for complicated environment, so we should not care about the initial value too much in practice. Epsilon greedy is simple and effective, but do we have any other choice? The answer is absolutely yes. We'll see two other algorithms. The first one is upper confidence bound action selection, and the second one is gradient bandit algorithm. The idea of the upper confidence bound action selection is to encourage the agent to select the action less selected. So let the NT of A represents the number of times the action has been selected prior to time t, and we put the NT in the divisor of this term. So we in addition to the original action value function Qt, we add a term that which is the long t. T is the time. So this term increased slowly, right? So with the longer the time we are playing, the more probability this action will be selected. But the most important is that the number of times being selected is in the divisor, which means if you are less selected, then you will have higher value and have higher probability to be selected. Another algorithm is called gradient bandit algorithm, and we can use gradient ascent to update our value function. Now we define a new function called the action preference function h, and we can update the function ht plus 1 of action A as the previous action t plus the, no, here is the key, plus the gradient, partial gradient of the reward, expected reward. Remember that we are always try to estimate the expected reward. This is our learning goal. And we use the partial derivative of expected reward over the preference function ht of A. So this derivative means that we can we will prefer that action that has larger relative probabilities. So we use, this is called a gradient ascent. Gradient ascent. And the expected reward actually can be defined is equal to the sum of actions, all actions. based on the policy pi x. Suppose all the actions in the action space based on the policy pi and the optimal action value function. So the expected reward can be reformulated as the sum of all policy function multiplied by the optimal Q action value function. Because this is the definition of expectation, right? The probability multiplied by the reward, by the value. So this is the definition of expected reward. Now we have the updated rules of our action preference function, which use the expected reward to estimate our action preference, right? To do that, we introduce a action probability function pi t, which can calculate the different probability of selecting the actions over an optimal select actions, and the action probability multiplied by the optimal value is indeed the expected return. This is the definition of the expected return. So now the problem becomes how to calculate the partial derivative of the expected reward. Actually, this function is equal to the optimal value Q star has nothing to do with our action preference function. Right? It's the optimal function. So our formula becomes let's rewrite x. So we only need to do partial derivative with our new function pi t, right, over our preference of action, and the Q star is unchanged. So how do we design the action probability function pi t of A? Pi t of A is the probability of taking action A at time t. So it needs to be a probability function which the output is between 0 and 1, and it needs to consider the preference of different actions. So the most popular choice, the go-to solution, is the Softmax function. You see this function again and again in neural networks, right? This is the go-to function for multi-class classification. So what is the Softmax function? The Softmax function takes k input, k real numbers as input, and normalize it into a probability distribution. So the output is between 0 and 1. So our function pi is actually a Softmax function. There is a trick which is called ending a baseline, which can improve our learning performance. Let's go back to our previous partial derivative of expected reward over the action preference. And we only need to do the partial derivative of our action probability pi, right? And in fact, we can, because we are using the Softmax function, we can add a baseline. We can add a baseline here. Baseline b is a constant, so we want our optimal value better than the baseline. Okay, we can add or not add this function, but experimentally adding a baseline can improve the learning performance. Here is another trick. After ending the baseline, we can multiply both terms of the sum with the function pi t of x. So is multiply the both term of the sum of the quotient with the function pi t. By multiply both terms with pi t, we can rewrite this summation formula as expectation. This is the definition of expectation, which is the probability multiplied by the value. So now we are going to calculate the gradient for only single action, capital A, T. This is because we can only select one action during our learning, right? One action at a time. So let's set the x equals capital AT and replace x with capital AT, right? In our formula. Then the optimal action, the optimal action value function, the optimal value for action capital AT is equal to the reward RT. Right? We are almost done, but there's one more challenge. We need to calculate the gradient of our action probability function pi, right? Which is equals calculating gradient of Softmax function. So to calculate the gradient, we need to recall the rule, the derivative rule of quotient. Right? This is equal to f prime. I use f prime to represent first derivative plus the first derivative of function of the divisor gx, and this term is divided by the square of function g of x, right? So now the fx is equal to the dividend EHTX, while the divisor is g of x is the sum of other terms. Okay. So now let's do the gradient. So this term, again, is actually equal to here the indicator function multiplied by the e of htx, right? So e to the power of htx. This is because the derivative of ex is equal to itself. So we can derive it here. The derivative of this term is equal to itself multiplied by this term, and this term is equal to the indicator function. I should say this is the indicator function that action equals x. So it is equals 1 if the action is our selective action A, or 0 otherwise. Okay, good. So let's continue. And for this part, now we can remove the sum of other action preference, right? So we will have these two terms. We can separate those two terms, right, into two independent quotients, and this is actually our original action probability function, right? Again, here is the multiplier of our original action probability function multiplied by the probability of action A. So eventually, we can simplify our equation as the action probability function multiplied by the indicator function minus the action probability of action A. So this is the gradient of Softmax function. So now we know the gradient of the Softmax function, we can update our formula using a new gradient of Softmax. So this is actually equal to the indicator function minus the action preference function pi of A, and we can remove both pi t of A t. We can remove both terms, and finally we get this simplified formula. Let's recall our original gradient update rule, the gradient ascent. We want to calculate the gradient of expected reward. So finally we get this, right? But actually, because we only care about the gradient, we can ignore the expectation and simplify our formula as the final term. The reward, the difference of the current reward with our baseline, and the indicator function minus the action preference, action probability function pi t. So this is our final formula of gradient bandit actions. We update our action preference function after selection and action AT, right? So if the current reward RT is higher than the baseline BT, then we update our function. We update the action preference of capital AT. We increase the action preference of capital AT, and we decrease the action preference of other actions. Right? So this is the final formula.